Hello everyone, and thank you all for joining us. Today's webinar, How to Reduce Small Appliance Noise Without Reducing Performance, is brought to you by Eastman. Your presenters today are Dr. Stephen Givens and Alex Dudal. Dr. Givens is a senior polymer application scientist responsible for new application development, market-focused research product development, and product performance for Eastman Triton copolyester. Joining Dr. Givens is Alex Dudal. Alex Dudal is responsible for market development activities related to Eastman copolyesters in non-food contact applications for consumer durable goods, including 3D printing, major appliances, and electronics markets. My name is Trey McDonald with UL, and I'll be moderating today's event. You can send us questions by typing them in the question box that's located on your screen, and our panelists will answer them at the end of the presentation. We are recording today's event, and we'll send you a link by email when the slides and video have been posted to the UL Prospector Knowledge Center. With that, I'd like to turn the presentation over to Alex. Alex?
Thank you, Trey. Before we get started, I want to say a couple of words about Eastman Chemical. We are a global specialty chemical company that produces a broad range of advanced materials, additives and functional products, specialty chemicals, and fibers. We are based in Kingsport, Tennessee, but we employ about 15,000 people worldwide at our 50 manufacturing sites and serve customers in about 100 different countries. We're also dedicated to environmental stewardship and social responsibility, which is why we have been named a responsible care company for more than 25 years. And just this year, we have been awarded Energy Star Partner of the Year. We've also been named one of the world's most ethical companies. And we've been voted number 11 by our own employees, number 11 best place to work in the United States through the Glassdoor website. So, to give you a quick overview of what we're going to cover today, we will talk a little bit about what consumers want, specifically in the appliances, small and large appliances markets. And then we'll focus a lot on really understanding how Eastman Triton copolyester can help enable improvements in acoustic performance in a variety of applications, as well as we'll briefly cover some of the other advantages Triton might have for those areas, including aesthetics, toughness, and durability. And then we'll wrap up with a question and answer session where we'll address some of your potential questions. So what do consumers want for the small appliance and just appliance market in general? Well, functionality will always be important. They would want their blender to blend and their vacuum cleaner to clean and dishwasher to wash dishes. But brand owners in recent years have done a really good job designing appliances that do their work really, really well, that provide variety of design options and colors, and provide variety of new additional features from variety of cycles to connected devices and things like that. So in this mature market, it becomes more and more difficult to compete and more difficult to come up with products that are differentiated and innovative. So a lot of other properties and a lot of other benefits become a lot more important outside of just functionality. One of those clearly is sound. In fact, I would say this is probably one of the next big areas where brand owners can differentiate their products. There's a large amount of research available out there that shows that consumers are actually willing to pay premium prices for quieter appliances, and that it really impacts the way consumers enjoy and appreciate their appliances. So just a few examples here. There's an Electrolux report on noise that was published a few years ago that actually showed that about half of the consumers are willing to pay 10% price premium for an appliance that's noticeably quieter but has the same level of performance. We'll talk about the second point in more detail in a second, but really for every 1 decibel that the noise rating for a dishwasher goes down, the price goes up by about $71, which is a substantial margin improvement. And then there's a lot of other surveys that were conducted that really show things like 39% of the people will actually avoid using an appliance at certain times during the day because of the noise they produce. And 62% of the people actually felt that noise from appliances adversely affected the enjoyment of their home life to some extent. So if you actually want your consumers, your customers, to use your products more often and enjoy them, certainly improving the sound performance of those appliances is a big area of improvement. So that was in general, but talking about a couple categories in specifically, we can talk a little bit about high-performance blenders, which is one product that certainly generates a large amount of noise for a very short period of time. So what we've done is we've looked at reviews for 12 different blenders on Amazon.com, and here's some criteria that we use. They all had a power rating of at least 1,000 watts. They were all priced at over $100, so it had to be a higher-end product. And we chose a variety of different brands, both more popular, well-known brands, as well as maybe less-known brands. And the other thing is each blender product had to have at least 50 reviews, so we had a good sample size. So what we did then is really just search for word loud within all those reviews to understand how often and in what context it was mentioned. That gives you a pretty good idea of how often consumers really think and equate, the noise level of the product when they actually rank and review your product. So before we go into the data, there's a couple more colorful, good examples that I think sometimes speak better than charts and graphs. So a few examples here. Obviously, one of the main things we learned is that consumers can be really creative when they review products online. So for example, comparing it to an F-16 taken off in the living room, while at the same time, something to note is ranking a product 5 stars. The second review there is really interesting because it actually, the reviewer actually says that the only reason they ranked a product 4 stars and not 5 was noise. So certainly that's one of the biggest barriers sometimes to really getting full customer satisfaction. That's a good example of that. And the third review is a good example because it underscores the idea that customers actually almost expect certain products to be loud. So a blender is loud, but which blender isn't? And again, if your goal as a brand owner, as a developer of new products, to actually delight customers, to surprise them, this is a good way to do that, to come up with a product that has unexpectedly improved sound performance. And then a few other colorful examples, comparing it to a jar of angry hornets, or worrying about going deaf, or comparing it to a tornado that might tear your house down. Obviously, all are very colorful, interesting examples. So now looking a little bit at the data, this will show you actually which blender models exactly we've looked at. They all had very good ratings, as you can tell. Most of them are over 4 stars on average, so these are well-reviewed products. And as you can see, across all categories, across all reviews, about 8% of reviewers actually talked about loudness of the product in some context. So you can see almost 1/10 of customers who review products think about, at least blenders, think about the sound level that those products produce. The other interesting point here to notice is that in the 4- and 3-star categories, especially the 4-star categories, those are the areas where consumers mentioned the product noise level the most. So as you can see, it's not quite as important in the 5-star and 1-star range. And this could mean that the reviewers that tend to maybe think more about it and put more thought into their reviews and potentially be more critical are the ones that tend to pay attention a lot more about to that characteristic. So now let's talk about a different product basically an opposite end of the spectrum when it comes to sound performance. So in the blenders, you have a product that makes a large amount of noise in a very short period of time. A dishwasher is a product that runs for a very long time and makes a relatively low amount of noise by comparison. So what we were able to do there, because most of the dishwasher products are fairly similar, there's a lot less variability in that than in blenders. They can be compared a lot easier. So what we've done is we looked at 172 different dishwasher models that were available at a large big box home improvement store in U.S. And we isolated about 12 to 15 different variables across all these product categories. Those included things like what color it was, where was the control panel, was it hidden or exposed, the number of wash cycles it had, the top material, whether it was metal or plastic. The brand was one of those, and the sound rating that provided for that product was also another one. So doing the regression analysis, what we were able to find actually is that sound performance out of all of those variables really had the biggest influence on the price of the dishwasher compared to all the other ones. That impact was also statistically significant, even bigger influence than a brand and other things. And basically the most interesting one is that on average, every time the sound level of a dishwasher went down by 1 decibel, the price went up by about $71. So there's certainly an opportunity to create products with higher margins and that consumers are going to pay for by improving sound performance. This is just a quick example that shows you what brands we've looked at and how the data looked like. Just a couple things to point out here. AGA and the core brands were actually excluded because most of the other categories, most of the other brands had a full range of products that went from, you know, lower price to high-end products. For those two brands, they only were premium categories. So that actually skewed data somewhat, and including those means that every time the sound reduces by 1 decibel, price goes up actually by $78. So at the same time, as you can notice, it seems that reducing noise in even a lower end of the range, so in an area where it's already fairly quiet, creates even more value. So that additional increment of noise reduction actually becomes more and more important the quieter the products get. And finally, you know, we can talk about reviews and price and things like that, but really, in the blender level at least, you know, it's pretty clear that there's certain opportunity for improvement when the products that are created currently fall somewhere on the noise scale between a lawnmower and an area that OSHA considers potential for causing hearing damage at a prolonged sound level. So now that we know that this is certainly an area that can help our customers, help brand owners differentiate their products, help create products that consumers value, what can you do about it? And this is where I'm going to hand over the presentation to Dr. Steve Givens to talk in detail about how Trident can enable you to improve those aspects of your product.
Thanks, Alex. Thanks, everybody, for joining us on the webinar today. I'd like to switch gears a little bit and talk about some data that we've developed looking at fundamental aspects of the way Trident dampens sounds that lead us to believe that it may be a pretty good, cost-effective solution in reducing noise in small appliances and other things like boom-mounted microphones that'll reduce feedback from sort of seismic interference. Can also cut down on the interference from say an over-the-head earphone that, you know, kind of noise that's impeding on that shell. So reducing noise in small appliances with mechanical motors is really the focus of this research. And an interesting phenomenon happens when you mount an electric motor to a hard surface. You essentially make that outer shell a resonator, like the body of a guitar. And so what happens is there's vibration that's provided by the motor that drives this appliance and gives it the function that you need. This vibration reverberates and radiates from the surface as an audible noise. There are a few ways to address this. You can reduce the vibration of the source. This usually entails having a less powerful motor, which often reduces the performance of your device. You can isolate the mechanical vibrations. This is sometimes done with rubber bushings. This is a good idea until you actually compress the rubber when you install the motor. Once you compress the rubber, it doesn't dampen nearly as well. And then the third choice is to improve the damping response of the materials that you use in the housing and the construction of the blender or any small appliance, really. So reducing noise in small appliance, we think that choosing materials with good sound damping properties is a simple and very cost-effective way to achieve substantial and noticeable reduction in the noise of a small appliance. And it's not actually only the noise level, it's also the frequency of that noise. We'll get into this data in just a second. So there's a range in human hearing somewhere between 2,500 and 5,000 hertz that's extremely irritating. That's the sound of nails on a chalkboard and babies crying and dogs howling. And a lot of the noise that's generated by a blender made out of engineering resin that has high modulus is in that irritating range. So to look at this, we decided to test materials to compare their damping properties with a number of specific tests. And then we'll look at these results that pretty strongly conclude that Eastman Triton copolyester compared to a number of competing materials has significant advantages in vibrational damping. So the test that we use to determine this advantage is what's called center point impedance measurements. This is sort of a crude diagram of how the test is done. So everything here is done in an anechoic chamber, so there's no interference from echoes or external noise, and that's in the upper left-hand corner, the picture in the upper left-hand corner of this slide. If you look in the upper right-hand corner, this is actually the sort of the test bed. So that round cylindrical object at the bottom is a frequency generator, or a shaker as some people might call it, that has an accelerometer built into the head. So you'll notice there's a panel of material that's mounted there. That's the material to be tested. So basically you mount this to this frequency generator. You apply that frequency to the material, and then with the accelerometer you look at the material's response to that frequency. And then the picture in the bottom shows the software and the sort of frequency splitters that are required to do all this in real time. And what you'll find out is, based on these center point impedance measurements, you can come to ultimately what's called a damping response factor. And so we use this testing to compare Eastman Triton with a number of other materials with this center point impedance test. And plotted on the graph, what you'll see in just a second is the materials that exhibit lower frequency response. That's to say that the peaks are smaller on the graph and they more quickly return to a baseline, have a better damping performance. And based on this data, which we have generated for probably a couple dozen materials now, you can calculate this loss factor, and materials that have a higher loss factor exhibit better sound damping properties. So ultimately, we take some very complex physics and we reduce it down to a number that you can use to compare a lot of things with. And again, the higher the number, the better the damping response. And so what we found is that Triton exhibits better sound damping properties against all the materials that we've evaluated so far. And it's an especially large advantage in damping versus things like polycarbonate glass, PCABS, some of the more common materials used in this space. So this is an example of that center point impedance test. This is the data that results from this test. This is kind of blown up to illustrate each individual peak and how the height of the peak and how quickly those peaks attenuate back to sort of a baseline, how important they are to calculating this damping response factor. This is blown up between 5 and 1,000 hertz. We actually run the test across the entire spectrum of human hearing from about 20 hertz to 20,000 hertz. And what this does is it illustrates how the material actually propagates this vibration through the material. And it can either increase or dissipate the energy, the frequency of that vibration, and also the speed of the vibration. And this is due to the viscoelastic nature of the material. And so it's a viscoelastic response to actually the energy being propagated through the material. And so what you'll see here in this slide, where we compare Triton with the blue line, Spectar, which is another Eastman material, in the red line, and Sobic Lexan in the green line, is that Triton not only vibrates at a lower frequency, it also, the peaks have less amplitude and they return to the baseline more quickly. And we'll illustrate that a little better in a bigger frequency range in the next slide. And what this is actually on the x-axis is force over velocity. So it's newtons per meter per second. So that's actually how the wave moves through the material, how fast it moves, and how much force it moves with, over the frequency at which the material vibrates. And so if we go to the next slide and we look at another consideration set where Triton again is in the blue line, ABS is in the red line, and glass is in the green line. This is the same type of testing over a wider frequency range from 5 to 5,000 hertz, again up to 5,000 hertz because that's the top of that really irritating range for human hearing. And what we heard, Alex was showing us some of the reviews that we found online, and one reviewer said, got this really expensive $700 blender. No matter where I run it in my house, it wakes my baby up. And this is an example of how that can actually happen. So you'll notice that glass, which people think is great at really blocking sound. It's good at blocking transmitted sound, but it actually vibrates quite strongly all the way up to 5,000 hertz, so all the way across that irritating range. And this is because glass is not viscoelastic in nature. It has no viscoelastic response. So it doesn't have the ability, like in this case, even ABS has a better ability to slow the force and the velocity of that wave down than glass does. And you'll notice again that Triton vibrates at a lower frequency here. The peak heights are lower, and that more quickly Triton reaches that baseline. So somewhere around 2,000 hertz to 2,500 hertz is kind of the last, vibration, the last peak you'll see for Triton. Whereas ABS here, has distinct peaks out to around 4,500 hertz. And so this is why a blender made out of these other materials is not only louder, but it makes a sound that may irritate you more, essentially, a higher, tinier pitch sound. And so basically we take this data, we use this data to compare Triton and our other copolyesters with other engineering resins. And the next slide is an example of the dampen loss factor summary of polycarbonate versus copolyester, so Triton in specific. And you'll notice here that each one of these vibrations, this is the first 8 modes, so basically the first 8 vibrations that you see in the previous 2 graphs. They represent most of the response, or they allow you to predict most of the response of the material out to, very far vibrations. And so you'll notice that at every frequency here, Triton is actually vibrating at a lower frequency. So the first mode is at 23. For Triton, it's at 26.5 for polycarbonate, all the way up to the 8th mode, which is 805.3 for Triton and 1,075 for polycarbonate. And so this illustrates, the higher pitch of that sound, the tinier, slightly more irritating part of that sound. And then the damping loss factor, so you'll notice for Triton it's 0.044, whereas for polycarbonate it's 0.007. So basically Triton has 6 times the loss factor, or over 6 times the loss factor of polycarbonate. And this higher loss factor indicates a better ability of the material to dampen sound created by mechanical vibration. And in practical applications where noise is generated by the housing of one of these motorized devices, or vibration, say, from a spoken voice is transmitted down the boom to a boom microphone, this ability to dampen that vibration makes things like a polycarbonate part perceived to be over 3 times louder. And so to understand that a little bit more, we did a very simple experiment. So we wanted an example of mechanical damping, of sound damping. And so what we came up was a rather simple example of a shaker. So you can think of a big baby rattle. And what we did was took a beer mug. We injection molded these beer mugs out of a bunch of different materials, probably like 12 materials now. We cut the bottom off of one beer mug and solvent welded it to the top of the beer mug, and we put some ball bearings in it, and that allows you to generate noise from this housing, so from the beer mug, by mechanically vibrating it with impact to the ball bearings inside the mug, in the closed mug. And so no matter how hard or soft you try to shake these things, there's a noticeable difference in sound quality. So it's, the irritation level and overall sound. And what you can see here is that, so the Triton mug shaken very vigorously, about as vigorously as we could shake it, 10 or so times, and an average came out with a with the decibel level of around 106, where the acrylic mug came out at 122.7. The methacrylate styrene mug came out at 124.9, polycarbonate 123.9, and SAN 124.6. And so it's important here to remember that decibel is a logarithmic relationship. So a 10 dB increase in sound is perceived by the human ear as being twice as loud. And so when you look at that 16 decibel difference between Triton and acrylic, roughly 16 decibel, translates it into being about 312% louder. And then MS is 363, PC 339, and then SAN 356. So these Triton shaker cups, they produce the lowest noise. They produce the noise that's a little more friendly in the frequency range, so it wasn't quite as irritating. And these other materials, you know, they're over 3 times louder than Triton. And so that's a good example of just pure damping. You can eliminate all the noise generated by the motor itself. You can eliminate, you know, all the noise generated by the blades, and it's just the ability of the material to dampen that mechanical vibration. And so to sort of summarize what we just talked about, dampen loss factor, before we move on to some more specific testing that we've done in blenders themselves is, again, when motorized equipment such as an electric motor is mounted inside a solid structure like the base of a blender or even a vacuum cleaner, energy can be transferred to the surface of that equipment, and then this vibration can radiate from the structure as an audible noise. Damping reduces the amplitude of these resonant vibrations. A higher damping loss factor indicates better damping, and the Triton damping loss factor is at least 0.044. And Triton's damping loss factor is significantly better than polycarbonate, glass, SAN, acrylic, PCABS, pretty much everything we've tested so far. So once we sort of developed this base data, we wanted to take it and apply it to real-world applications. And so we were most interested, and the focus of this presentation is around high-powered blenders. So what we did was we went out and bought 16 blenders on the marketplace. So they're complete blenders from their manufacturers. And what we really wanted was that source of vibration. And the source of vibration that causes pretty much all the sound in the blender is the motor. And so if it's the base vibrating or if it's the impact of the food to the jar, all that energy is still coming from the motor. And so what we did was we bought these motors, or we bought these blenders. We took the motors out of them and whatever electronics that was required to make them run. So that's the picture in the lower left-hand corner of this slide. And we built boxes out of different materials to mimic the housings of these blenders. So we didn't have any way, we didn't have any molds to actually make a blender cover or a blender housing. So we built boxes, and in order to do that, each motor is unique. And so you can see in the bottom right-hand corner here, there's a picture of several of these motors. Each one is made differently. Each one is mounted differently. So when we took them out with their electronics, we had to build a mount out of each material we wanted to test for each blender. So, and then we performed sound testing. And so the way we did that is we mounted these motors in boxes, and here we're going to talk specifically about a box, a 6-sided box made out of Triton, one made out of polycarbonate, one made out of PVC. And so you can see each material is mounted on a mount that's unique for that motor and is mounted directly to the box. The only thing that the only other thing we kept is the electronics, so like a override circuit to make the blender motor actually work. And so this allowed us to engage that motor at full speed, 100% output, which allowed us to generate those vibrations like you would in a blender that would cause the box to vibrate, create that audible sound. And so we did this for a series of materials. Here again, we're going to talk about Triton, PC, and PVC. We very carefully took measurements from the box. So in this consideration set, we're going to talk about 6 blender motors. They ranged in power, and we took 3 readings each from the top the front, top, and the back. We averaged those out. We were very careful to keep the decibel meter at the same distance from the box, which in this case turned out to be about 4 1/4 inches. And we did all these measurements in the dBA weighting system, which is the most common measurement scale in dBA, and it's also the one that's designed around conversational use. So what you'll see is that from the 6 different models, where Model 1 was about a 900 watt power motor up to Model 4, which was about an 1800 watt motor, you'll notice that the noise emanating from this box, from the vibration caused by that motor, Triton is the quietest, and in some places it's significantly quieter. So in Model 1, Triton is about 14 decibels quieter than polycarbonate. In Model 2, you see a bigger gap between PVC, but again, because of the viscoelastic nature of Triton, kind of that unique backbone that's proprietary to Eastman, Triton is very, very good at damping vibrational energy. So once we developed that, and we thought, the fundamental tests are falling in line with what we're seeing in the real world, is what we're seeing with our shaker cups. We had customers that asked us a question, well, okay, so you can give me 6 or 8 or 10 decibel reduction by switching from, say, PCABS to Triton in my base. What if I need more? And so what we wanted to do was develop a relationship to look at how we could reduce noise even more. And so what we did is we built a box. This again is a 6-sided box. This one we insulated with acoustic foam to make it a semi-anechoic chamber, and we put blender bases in that were not disassembled, so fully assembled blender bases. We took the same type of reading with the same type of decibel meter, also again in dBA. And this time we looked at, in this consideration set, we got about 9 blenders ranging from about 550 or 600 watts from brand 1 up to 2100 watts or 2200 watts for brand 9. And again, you'll notice that if you increase Triton's thickness by 2x, you'll see about a 6 dB reduction in noise. So if you look at that first column of numbers, the first column is at 1/4 or 1/8 of an inch in thickness, and then if you go to 1/4 of an inch in thickness, you get a reduction of about 6 dBs across that line for brand 1. That holds true all through all 9 brands here, through all different watt ratings of the motors. And then if you increase Triton's thickness by 50%, you see about a 3 or 3.2 decibel reduction. And that also holds true across all these 9 brands. And so finally, we were able to find a real-world comparison. And so this is 2 blenders made by the same company with exactly the same motors, exactly the same blades, exactly the same everything. The difference is the blender on the left, the jar is made out of polycarbonate at about a 3 millimeter thickness, and the blender on the right, the jar is made out of Triton at also, again, about a 3 millimeter thickness. And what you'll notice from the decibel meter is running at full power, blending popcorn, which is our analog for a really hard food stuff, is that the Triton blender is 4 decibels quieter. I should say the blender jar is 4 decibels quieter than the polycarbonate blender jar. And so that's purely from just material change, from a stiffer material that doesn't do as good a job damping to a material that does a better job damping. And so 4 decibels, again, that's about a 32% reduction in the loudness of this blender. So it's extremely noticeable. So I think, we've done a pretty decent job of presenting some data that shows that vibrational damping is advantaged in Triton copolyester. There are other things that make Triton compelling for this market space also, and I'd like to segue a little bit and talk about some of those. So home devices, especially kitchen devices, they spend a lot of time in your counter. People spend a lot of money on their kitchens. They spend a lot of time enjoying cooking and eating in their kitchens. So aesthetics of all these products becomes extremely important. And one thing you'll see with Triton copolyesters has excellent aesthetics. So our little chameleon friend here is standing on a bunch of Triton color chips, and you'll notice how vivid and glossy these colors are. And you can see the color tablets in the bottom left-hand corner. It's pretty striking that you can actually see the reflection of the white tablet in the face of the black tablet. Most of our customers refer to the look of these opaque Triton housings as a wet paint look. So it allows you to make a really vivid, beautiful, glossy color that's created, straight out of the mold. So a lot less expensive secondary operations, so you can skip painting steps and some coating steps and maybe even some in-mold decoration or in-mold labeling steps. So Triton really allows you to make appliances that look as good as they sound. The copolyester, Triton copolyester allows you to create devices that have very vibrant colors and outstanding gloss that beauty will not fade. It won't crack or haze to exposure to chemicals and common foodstuffs, even household cleaners. We also have excellent design and tech service to help you achieve these aesthetics without having to paint or use secondary operations. And then Triton also performs very well in a variety of secondary operations. So you don't totally lose that possibility if you want to do things like in-mold decoration or hard coatings, surface texturing, or painting. Those options are still there with Triton. And so toughness and durability, it's an interesting aspect. Copolyesters in general, and Triton especially, is known for being extremely tough and durable. And so toughness and durability, they're used interchangeably, but they're really not the same thing. So, a tough material may not be durable when it comes to exposure to certain chemicals or exposure to certain foods. It may also, the mechanical properties may not be really on par with everything else. And so here's just a simple comparison between a couple of different grades of PC-ABS, which are common in this market, especially in the housings, and Triton. And so you'll see that break stress, everybody's kind of on the same level, but break elongation really stands out for Triton, 216. Modulus is a little less for Triton, but that's one of the things that allows it to be so durable. Notched izod, so if you want to think purely about impact, notched izod is outstanding. So is multi-axial impact, really good. Heat deflection temperatures for Triton are also, very respectable for this type of market. So Triton is extremely hydrolytically stable, does very, very well in the dishwasher. And so I think this really illustrates the point that durability goes beyond just mechanical properties. And mechanical properties don't often tell you the whole story. I mean, they're very good on a data sheet used to compare two materials, but material performance can be impacted by a lot of things, especially the exposure to chemicals, stresses, whether either applied stresses or inherent stresses. Cold temperature performance varies widely, and so does hydrolytic stability. So one thing that copolyesters have been known for years, 40 or 50 years, is a chemical resistance compatibility. And we look at this on an ongoing basis. We have an enormous database of chemicals that we look at, not only for our own interest, but the interest of our customers. And we like to use, rather than pure tensile testing, which is maybe not as applicable in the real world, we like to use what's called CEAST, reverse side impact testing. So CEAST is an instron method, and basically what you do is you apply your material to a strain jig, so you can, typically we use a 1.5% strain, so that implies some stress that's being put on by the real world. We then saturate a pad of cotton and put it on one side of the material, and so that's going to induce some cracking or crazing if there's a chemical attack. That's represented in step 2 in the upper right-hand corner. And then we impact the back side of that flex bar, so the side that is not exposed to the chemical, and that way we can put the chemical exposure side in tension. And what we do is represent this data in the form of retained impact strength versus a control that has been strained but has not been exposed to the chemical. And so this is just a rundown. We won't go through each one individually, take way too much time. This is an example of some common things that all engineering resins are exposed to and sometimes don't fare very well, starting with skin oil. So if you think of a headphone or an earbud application, you know, a lot of contact with skin oil. Polycarbonate, ABS really suffer. Some grades of polycarbonate, I should say, and ABS really suffer. Whereas Triton, at least the standard flow and the high flow grade are pretty immune. And you can go all the way down the line here, and what you see is that the Triton family, there are things it's susceptible to, especially sunscreen. But you know, the majority of the time, Triton survives this exposure. And so we feel that, you know, that really speaks to the durability of this resin in this type of space. And one example here is of an applied stress is simply a 1x1 plaque that's had a hole drilled in the center of it, and then we put in a stainless steel bolt, and we torque that bolt to 85 pound-inches of torque, and we spray it with Windex, the multi-use disinfectant cleaner that you'd see a lot in the kitchen, and we let it set out for 48 hours. And so you'll see the polycarbonate, because this is a clear plaque, you can see the actual stress cracking induced in the polycarbonate, whereas the Triton copolyester doesn't crack. Now in an opaque housing you might not be able to see this, but that's what's happening in a lot of appliance failures. If you get a housing crack or a housing that starts to chip, it's actually this environmental stress cracking that is sort of masked by the opaque nature of the material. So just to summarize toughness and durability, Eastman Triton copolyester has a unique combination of toughness, chemical resistance, and low stress level. We didn't talk about the stress level a lot, but that last slide kind of illustrates it. And Triton allows brand owners to create devices with housings that will maintain their integrity, you know, through their intended life in increasingly harsher environments.
So just to wrap it all up before we go to the Q&A session, I have one last video to show you. So Triton historically has been really known for being really tough, really clear, BPA-free material that's used in a lot of dishwasher durable applications. However, what we want to get across is there's a number of other applications and advantages to using Triton in more opaque housings and in other type of applications outside the jar. None the least, reducing the sound and improving the sound quality of those appliances. More important, you can use Triton both in the jar and the housing of appliances and other parts as well. And if you use Triton in both of those applications, you actually substantially improve and, you know, enable a better acoustic performance than using one or the other. And ultimately, if you make products that consumers can enjoy more, that produce better, higher quality sound, they will appreciate that, they will value that, and that's ultimately what all the brand owners are looking for.
All right, guys, so we are actually going to move into our question and answer session when we give both Alex and Steve a bit of time to review some of the questions that we've had come in. We've had a number of great questions already come in, so please do continue to send those. We've got some great technical experts on the line with us here. Just a reminder, we will be sending you guys a copy of the recorded video presentation as well as the slides, so do be checking your email for that in the coming days. And we do have a short 3-question survey that we would appreciate your feedback after the webinar. But we've had a number of great questions already come in, so we'll turn it back over to both Alex and Steve, and we can get started with those questions.
Okay, thank you, Trey. Yeah, we had a good number of questions, so we'll try to go fairly quickly to try to cover them. So the first question was for the frequency response factor that we talked about, how does that really correlate to delta from the 10 delta from the DMA analysis? Steve?
Okay, so 10 delta is sort of a broad indicator of damping response factor. It's not, I would say it's indicative, but it's not a good quantifiable relationship. So when we first started this work, we initially looked at 10 delta, and we saw that we had, we thought we had something that was interesting, but ultimately 10 delta wasn't sensitive enough to give us the individual responses of these materials to the frequencies.
Thanks, Steve. So the next question is, for the damping analysis, again, why not run that test at the same frequency?
Well, we don't run the test at the same frequency because motors don't vibrate at one frequency, right? So what we're really interested here in sounds don't often happen at a single frequency. So when you speak, there's a variety of frequencies. When you listen to music, there's a variety of frequencies. When you run a motor, an electrical motor, or even a gasoline-powered motor, there's a variety of frequencies that come out. So blenders in specific, you start at a peak load, and then as the blades start to engage the food and chop it up, there's a frequency range that all these things operate at. And so, the other important, so that's the input, so all those frequencies vary. We wanted to see how that varied from the output. So we wanted to see, we looking at these responses and through Amazon reviews and online reviews, you hear that some people really complain about certain blenders and the way they sound, and we wanted to understand that. And so part of that is we looked at the entire frequency range that the motor could produce, and we looked at the entire frequency range that the human ear can hear. So that's why we ran it over these frequency ranges rather than at a single frequency.
Okay. Thank you. Okay, another question was, so you mentioned that damping is related to viscoelastic behavior. How do the long-term dynamic mechanical properties, or also known as vibration resistance until breaking, compare to this?
That's an excellent question, and I don't really know how to answer it. So we've looked at depth into damping response factor, but I'm not at all sure how that relates. So it's something, if you want to contact me after the webinar, we can get into more in-depth conversation, even plan to generate some data. But right now, I just don't have any data to draw a conclusion with.
Okay. What is the intrinsic material character that differentiates Triton from other materials to contribute to a better damping of sound? Is it due to the specific formulation or something else?
So we definitely think it's due to the unique chemical composition of Triton. So Triton is a fully amorphous material, so there's no crystalline structure, even in small quantities, and it's made with one proprietary monomer that's kind of unique in its structure, and we've been able to tie a lot of the damping response to that unique monomer. So you'll notice that in that first consideration set in the center point impedance, it was comparing Lexan, Spectar, which is another Eastman copolyester, and Triton. And Spectar, the other copolyester, does not include that unique monomer. And so you'll notice that Spectar, while it was pretty good at damping, wasn't as good as Triton.
And just to add to that, there's obviously various grades of Triton available, and the damping performance between the neat grades of Triton is not that different. So most of the grades will offer that same damping advantage, and they will all differentiate from other competitive polymers. So the other question was about specifically UV resistance and specifically how do the colors react when exposed to the sun radiation.
So in the opaque colors, they're fantastic. You know, like all copolyesters, like almost all clear engineering resins, exposure to sun causes a little bit of shift, mostly to the yellow end of the color spectrum. But we really don't see that in our opaque grades. So you'll notice the examples that we gave specifically are kind of that ultra white color. Some people call it Corian white or the piano black. We've had those in testing for I think exposures up to probably 20 years, and we don't see a lot of color shift. So very stable. We do have UV resistance packages. You know, if you're going into a more harsh environment, like say if you think about putting a blender on a deck in, you know, Venezuela or something, very near the equator, not a lot of cover, we do have UVI packages that are available.
And is Triton UL certified?
Triton is UL certified. We have HB, UL94 HB grades and UL94 V2 grades of Triton.
Can you ultrasonically weld Triton?
You can ultrasonically weld Triton, one of our biggest applications and probably our biggest single Triton customer. Everything they produce is ultrasonically welded. We've actually developed a pretty decent data package around that. We'd be happy to share it with you. So just contact one of us. We've got very specific guidance on power of the welder, fixtures, weld joint designs, and spatial requirements to ultrasonically weld Triton.
Okay. And so obviously we presented a lot of data specifically comparing Triton to materials like PC and PVC. What about comparing Triton to crystal polystyrene, and specifically in terms of noise frequency reduction as well as impact properties? How would that compare?
So crystal polystyrene, so you know we've talked about damping is a viscoelastic response. Crystal polystyrene definitely has a viscoelastic response, but it tends to be a really stiff material, and so there's some relationship with modulus to damping, and usually the higher modulus, the less well the material dampens. That's a very broad generality, but in the case of like crystal polystyrene, this definitely holds true. It's a stiff material, so it doesn't dampen particularly well.
Okay. And how about the fatigue performance for copolyesters?
Copolyesters, they fatigue very well. They have really good fatigue response at low temperatures down to -40 C and up to probably you know 20 or 25 degrees below their glass temperature. So somewhere, or glass transition temperature, somewhere around 100 degrees C. You know, they're extremely tough materials. You'll see that reflected in their notch IZOD impact data. The one caveat is because they're amorphous, they don't stress whiten, they don't stress crystallize. So the fatigue is very good in a copolyester. The one caveat is if you're thinking about something like a living hinge, that is one place that we do fail. So you might get 2 or 3 or maybe even 500 bends out of a living hinge, and then it's going to start to neck, and somewhere north of that, maybe 1,000, you know, it's actually going to fail. So we don't have the performance, that fatigue performance like something like an olefin, but for an engineering resin, it's pretty good.
Would we recommend Triton for containers and pockets for refrigerators?
Yeah, actually Triton does very well in refrigerators. We're starting to move into the refrigerator space, into crisper bins and egg holders and all those sorts of things in the insides of refrigerators. Again, it has very good low impact properties. That sort of ductile to brittle transition in Triton and copolyesters happens at very cold temperatures, somewhere minus 30 C or minus 35 C. So down to about, minus 40, you have very good impact properties.
Okay. Somewhat related question. So what other applications beyond blenders might the acoustic properties and those values be important to? So I'll weigh in on that, obviously, a little bit. Really, any product that generates noise specifically from mechanical vibration, that would be a big advantage here, right? So specifically, what we noticed is obviously in terms of appliance space, it's very important for appliances that produce very large amount of noise, like blenders, for example, but it is also really interesting from the other perspective, appliances that either produce noise for a very long time, even though it might be lower level. There's a lot of value in that. So we talked about dishwashers, and other examples of that could be things like, especially robotic vacuum cleaners, the new type of product categories that tend to run for a long time, like an hour or two around your house. And even though right now, for vacuum cleaners, we expect to not do anything else while you're using it. But now you have a robotic vacuum cleaner as an example, and it runs while it allows you to do something else. So you really don't want to have a lot of noise while you're watching TV and it running. Other cases, especially anything that runs at night, any kind of appliances that runs at night, it becomes very important. So air purifiers, humidifiers, fans, those kinds of things, and they all produce noise from mechanical vibration. And then by extension, anything that goes into the like hospital rooms in the medical space, especially sleep apnea devices and things like that, that again are used at night, and they have pumps and gears and motors. So anything related to products that have motors and pumps and things like that. But then on top of it, Steve mentioned a couple. You can look into more acoustically related applications like headphones, especially with microphone booms that could potentially transmit vibration and cause some feedback sort of into the microphone from the headphone. I don't know, Steve, if you have anything else to add to that.
Yeah, I think robotic vacuum cleaners, that's a great area. Also, regular vacuum cleaners, they're loud. My dogs hate them. So that, that might be an opportunity. Anything that runs for a long time. So we've even started to think about housings for compressors and say like a refrigerator. Also, speaker enclosures, there may be some advantages there. So you think, historically speakers were made out of wood, and now they've gotten smaller. You don't have those big volumes to attenuate some of those noises that you don't want, so maybe it's more critical in the smaller speaker housings, especially things like a bass module, for like a surround sound system. I think that's an excellent opportunity. Things like Bluetooth headphones, Bluetooth microphones, for telecommunication. I think that's a good opportunity. We've seen that there's some advantage in that, reducing that sort of seismic interference that you get with a boom microphone. So that's all I can think of off the top of my head.
And then probably last question, since we're almost out of time, is so for all those applications, can Triton be used in more internal components as opposed to something like a housing in a jar, also helping reduce sound?
Yeah, that's we have a large and vibrant compounding effort here where we're starting to put things like glass fiber and reinforcement and carbon fiber reinforcement, things like nano clays. We started looking at Triton blends, so Triton blended with stiffer materials like ABS and polycarbonate, so you can still retain some of that damping response, but you can get a stiffer material to say make a motor base out of, or if you need a gear or a spline or something, to mechanically convey the energy from that motor to the blades in the blender, or mechanically convey that the power from the motor of anything to anything else, say to drive a belt in a vacuum cleaner, a robotic vacuum cleaner. We started to develop grades of Triton that can work in those applications.
Okay, well, I think that was our last question, so thank you for great questions, and thank you, Steve.
Thank you, Alex.
All right, everyone. Thank you all for attending. Again, just a few reminders. We do have a short survey we'd appreciate your feedback on. I also encourage you to check out some of the other Eastman presentations that we do have available on the Prospector Knowledge Center A lot of great informative presentations there, so we do encourage you to check those out. Again, we will be sending a copy of the recorded presentation and the slides so you can view that again and also share that with others at your company. But everyone, thank you for attending and have a great rest of your day.